Hey folks, how y'all doing? Um, we are getting to the last of our units on the Enigma machine. We're going to get started in a moment. I just want to remind everybody that you do have a um, written assignment that's due this evening. And if you've got questions about it, um, get in touch with me. All right, good luck. So last time we talked about Rejewski's theorem. We say that a permutation is of matched cycle type if and only if it's the product of two proper involutions. Match cycle type means that the cycle type, whatever the cycle type is, let's say, this is x1, then there's another cycle of length x1. And then if there's a cycle of length x2, is another cycle of length x2, and so on. That is that um, whatever cycle lengths we have in the cycle type, we always have them in pairs. Uh, and we did an example that was similar to this last time, but this one's a different example. This was number 2, um, where we're going to be able to write this permutation as a pair of involutions. And so what we're going to do is we're going to write um, pairs over each other. So we're going to match up the pairs. So HRU and JNS, these two have to match together. The BI and the TW, BITW, I can pair them up however I want to. I can choose to pair up the B and the I, or the B and the T, or the B and the W. And I can do the same thing with these 4 things here. There's no, when I have 4 of a cycle type, I can match them up however I want to. So, I don't want to write alpha yet. So I'm going to write B over I, and then T over W, and then HRU over SNJ. When we write one over the other one, the one on the bottom is in reverse order. You couldn't tell that with the first 2, but we can tell it now. And then we'll match up ACDO. Let's match this up with PQVX. So XVQP, just to show you that you can do this. And then EFGM then has to match up with ZYLK. Okay. All right, that's a P. And now we're going to write 2 permutations, alpha and beta. And alpha is just going to be the pairs reading straight down. So B goes with I, T goes with W, H goes with S, R goes with N, U goes with J, A goes with X, C to V, D, Q, O to P, E to Z, F to V, G to L, and M to K. The beta reads up and to the right, but does not cross from one cluster to another. So if it reads off the edge of a cluster, it then just wraps around back to itself. So I goes back to B, and W goes back to T, but then S goes to R, N goes to U, and then J is the one that wraps back around to H. So S goes to R, N goes to U, J goes to H. And then we can follow that same pattern here. X to C, V to D. Line that up here, V to D. Q to O. And finally P to A. Then the last one will be Z to F, Y to G. That's a Y and not a V here. Should be a Y there also. L to M, and then K wraps back around to E. We want to write sigma as a product of two proper involutions. Sigma is equal to beta alpha. We do alpha first, and then we do beta. So let's just try a couple of examples and show why this works. So if we look at beta of alpha of one of these fixed characters, for example, W, alpha sends W to T, so alpha of W is T, but then beta of T is W again, because they switch W and T and then switch right back. So then beta of T is equal to W again. So we started with a W, we ended with a W, and that's exactly what a fixed point is supposed to do. Let's try one of the non-fixed points from a cycle at the top. So let's see if U wraps around to H like it's supposed to. So let's look at beta of alpha of U. Alpha sends U to J, so that's beta of J. But then beta sends J to H, and so we do get H. U goes to H. Let's try that for the entry on the bottom row. Does S wrap back around to J? Beta alpha of S. Alpha of S goes to H. So this is beta of H. And then beta of H is over here, and H goes to J. So that's equal to J. And so, I'm not going to test all 26 letters of the alphabet, but we've tested a few cases here, and they all seem to check out. That we do end up getting the correct thing that sigma says that the letter was supposed to go to. All right? That's how Rejewski's theorem works. If we have a matched cycle, we can break it up into two separate proper involutions. So let's review how this applies to the ENIGMA machine here. When a user presses a key on a working ENIGMA machine, the rotors advance one position. A signal goes through the plug board. The plug board is actually down here, but it's represented up there again as well. Then the rotors, then the reflector, back through the rotors, finally back through the plug board, and then it shows up and lights up a letter. The daily settings include a start position for all the rotors. The Germans knew that encoding messages over an entire day using that same setting would provide the Allies with enough encrypted text to use an index of coincidence attack. And so they did something peculiar with this three-letter ground setting here. An operator would choose a different three-letter key for each message. The operator would use the ground setting only to encode the key. So we would use VYJ to encode whatever key the operator chose. So if the operator chose AXL, then we would set the machine to VYJ, but we would encode AXL. Then to ensure the key was transmitted correctly, it was set twice so that the receiving operator could check that the keys matched. Only 6 letters were encrypted in the ground setting, and since those 6 letters were random letters and didn't form real German words, that it didn't have to match with the index of coincidence. So that was because the index of coincidence is an index for actual text of a language, not just for random sequences of letters. So that was the idea, that encoding a separate key using the ground key prevented the ground key from being compromised. That's what they had planned anyway. Like I said, not like I said, but like I said in the slides, in 1940 they changed this procedure a little bit, and we're not going to have time to go through all of the different modifications they did over the course of the war, but this was the basic idea. So if the ground setting for a machine was VYJ, and the encryption operator chose the setting UHB for this message, the operator would set the rotors to VYJ. My pen is just messing up today. Let me just start the whole thing over. Set the rotors to VYJ, and then the operator would type UHB, send the new key twice, that way you had a check for it, and then would manually reset the rotors to UHB, and start typing the message. All right. So the decryption operator receives a message. Doesn't know the code UHB though. Only knows the code VYJ. So the decryption operator sets the machine to VYJ, types the first 6 letters, and the operator then reads this input, UHB, and then that tells the decryption operator to set the message, set the settings to UHB, and then type the rest of the message. That's the idea. And so that's how the decryption operator discovers that the key for the actual message is UHB. So let's look at a couple of observations for what happened here. One, no letter ever encrypts as itself. That is because of the way that the reflector worked. The reflector took 26 inputs and paired them up, so on and so forth, in some way. But whatever passed through the rotors the first time, because it gets reflected at a different location, it will pass through the rotors the second time in a different way. And so if you hit an H on the keyboard, you would not get an H to light up. No letter ever encrypts as itself. So here's one example of how that helped. We have a station that traditionally sends out a weather report each morning. And we find that the station has sent out a message that begins with these characters. Now, we expect that the word weather is going to appear somewhere at the beginning of the message. That's going to say something like weather report for, Wednesday, March the 3rd or something like that. But in German. Well, the word weather can't be at the very beginning of the message because that would make the E and the T encode to itself. Can't be the second letter, begin at the second character, because then these letters would encode themselves. Can't be at the third position of the message, because these letters would encode themselves. Can't be at the 5th or the 6th position of the message, but it could be at the 4th position of the message, because no letter encrypts as itself at that point. And so I've cut off some text here, and I apologize for that. But if we know with a high degree of certainty that some word will show up in the plain text, we can come up with a small set of guesses for where that word might actually show up in the ciphertext by sort of sliding the text, plain text, along the ciphertext and ruling out the places where it can't show up. And now I know I've broken 6 of the characters in the code, and that gives me some information about maybe the possible rotor positions or the possible message settings that have been used, because this will rule out some possibilities. The other observation is that for every possible key, the encryption by that key is an involution. And so here's sort of short proof here is that the permutation generated by the plug board, that's the first thing that happens. You hit a letter, it goes through the plug board, then it goes through the 3 rotors, then it goes through the reflector. And since I'm using R for rotor, I'm using M for mirror instead of reflector. But then it went back through the rotors and then back through the plug board. But this is a conjugate of a conjugate of a conjugate of a conjugate. This is just one big conjugate of M. And one of the things we learned 2 days ago, or 2 periods ago, was that conjugates do not change cycle types. And so the encryption of a message has the same cycle type as the reflector, and the reflector is a proper involution. And so I know that every encryption is a proper involution. Now, by Rejewski's theorem, the composition of 2 involutions is a permutation of matched cycle type. And so the composition of these 2 involutions will be of matched cycle type, and these 2 involutions, and these 2 involutions. So if I number these 1 through 6, the combinations of permutations 1 and 4 is a matched cycle type, 2 and 5 is a matched cycle type, and 3 and 6 is a matched cycle type. So the repeated message key at the beginning of the message gives us a composition of 2 involutions. This is kind of big here, because we gather a lot of these over the course of the day. That on the same day of the war, if the Allies are listening for transmissions, we might get several of these messages. And this gives us enough information to reconstruct these combinations K4 and K1, K5 and K2, K6 and K3. Because each of these is an encryption of something of the form XYZ, XYZ. And so I'm using K down here. K1 switches G and X, and then K4 switches G and X back. K2 switches A and Y, but K5 switches S and Y, but the Y is included in both of these, whatever letter it is. It may not be XYZ, XYZ, it may be, ADQ, ADQ, but then it's still the same letter at positions 2 and 5. Knowing that it's the same letter at positions 2 and 5 allows me to eliminate that letter. I want to do an example. I don't want to use the first one because of the repeated G. So let me look at the second one here. What we know is that for the second one here, K1 sends some letter X to O. I don't know what it is. And K4 sends that same letter X, but it sends it to a P. What that tells me is that K4 of K1 of O, K1 sends O to X, and K4 sends X to P, and so K4 through KO sends O to P, and so K4 composed with K1 is going to be some permutation that starts out sending, I've got it backwards, O to P, and so on and so forth. Okay. So let's see if we can finish this up. K4 composed with K1 sends the letter O to the letter P. So what I'm using is that O goes to P. So now I'm going to look through this same group of 65, I think it's 65 bits of ciphertext and see if I can find one that starts with a P, and I do. P has to go to S. All right, let's see what happens to S. Can I find one of these somewhere that starts with an S? And I do. S goes to A. Now I find one that starts with an A. Right here, A goes to T. Now I find one that starts with a T. T goes to W. W goes to R. R goes to N. Starting to run out of space here. I hope I can close up the cycle soon. N goes to Z. Where do we have one? Z goes to K. K goes to O. And so that closes up this cycle. All right, so now I look for a letter that I haven't used up yet. I've got O, P, S, A, T, W, R, N, Z, and K. Well, I already know from the first one that G goes to itself, so I'll go just put that G goes to itself. That's a one cycle. So let's look at the next term. V goes to L. L goes to Q. Q goes to D. D goes to M. M goes to... Do we have one that starts with M? Yes, we do. M goes to F. F goes to E. E, I know we have one that starts with E. I saw it earlier. E goes to U. U goes to J. J goes to B. All right, B had better go back to V, and it does. Here it is. B goes back to V and closes the cycle. And the reason I knew that is that I am looking for this to end up being of matched cycle type. And since there were 10 letters up here, there need to be 10 letters down here. All right. What letters do I have left? Y goes to itself. So now we have a match for the single letter G. We know that Y goes to itself. I have C goes to X. And I don't have C and X yet. So C goes to X. And X goes back to C. Okay, so now I have 10, and 10 is 20, 21, 22, 23, 24 letters. So there should be two more letters that I haven't accounted for yet. They need to pair up. So we have used up A, B, C, D, E, F, G. I don't think we've used up H yet. H right here goes to I, and I goes back to H. And so what we have done now is we have identified exactly what the permutation K4 composed with K1 is. That doesn't narrow down exactly what K1 is or what K4 is, but there are now only a certain number of possibilities, because we know by Rejewski's theorem that we just then match these up, one on top of the other. The trick is going to be this 10 cycle, because where's my pen? There we go. I can write a cycle starting at a bunch of different places. I could have written this, instead of starting with a V, I could have started with the L. That's the same cycle, but it's starting with an L. And so when I write one on top and one on the bottom, but the one on the bottom goes backwards, I can choose any of these as a starting place when I start writing backwards. And so there are 10 different ways that that top cycle and that bottom cycle could match up. And so, but 10 ways is not too hard to brute force. And then there are two ways that these two cycles can pair up. Again, I'm looking for my pen. Way over there. Sorry about that. Two ways that these two cycles could pair up. And so we have 10 ways of pairing these up, 2 ways of pairing these up, only one way of pairing these up. So that's still 20 possibilities for what K1 and K4 could be. But 20 possibilities is not going to take us that long to test out by hand. We have narrowed down to 20 cases what these two permutations do. That gives us a lot of information. We are narrowed down a problem that was originally 26 factorial possibilities and shrunk it down to 20 possibilities that we will have to brute force and check out by hand. And what will help us brute force it is this other observation that if I can match up any plain text with the messages as well, then I can eliminate some possibilities. Okay? So keep in mind that we can do this not just for K4 and K1, but we can do this for the next pair and then the next pair after that. Once we have connected enough examples that we can reconstruct this composition, then we can almost, zoom in on the individual permutations themselves. And that gave us a lot of information. All right. That's going to be it for now. Have a great day. Take care.